So we are in photoelectric effect, just started, and the basic concept we had. We'll have a quick recap of that. Means if we are having any metal, photoelectric metal, on which the light is falling, you will find that photoelectrons are being emitted out of the surface. How come? Because the metal will have free electrons. Free means doesn't mean that it can easily come out. Free means it is just the outermost electrons in the orbit of a particular atom. They are free to move from one orbit to the other orbit of the other atoms, not the same atoms. So in between the atoms, the electrons, their valence electron, they are sharing each other. They are just jumping from one to the other. So that way they are free. Now these electrons can come out if the light energy is falling on it. That is the photoelectric effect, right? And the electrons which are coming out, they are known as the photoelectrons, because it is after all happening because of the light only. Is it clear? Things are
Yes.
clear to you up to that?
Yeah.
So here in the figure arrangement, you see we are having the left bottom, you are able to see the figure. We are having the cathode and then anode, right? Cathode is a material on which if the light falls, it is going to emit the electrons, which will be known as photoelectrons, because it is due to the light, right? And then once it has come out of the surface of the cathode, I mean the metal, it is free to move. The other end, we are keeping the anode. Now anode, we can keep a positive, we can keep at positive potential. Photoelectrons being negative charge, it is going to be attracted towards that. So anode is kept positive in with respect to cathode. So what we'll be doing, we'll be simply connecting your this anode with the battery, positive side of the battery, we can say, right? We can just connect with the positive side of the battery. Like here we have connected. Arrangement you have seen, right? Now we are having RS. This is the switch. If you want, you can make the anode at the negative with respect to the cathode, so that you can control also the electrons which are coming towards the photoelectrons which are coming towards the anode can be controlled. If I am keeping the negative potential or zero potential or negative potential, rather, you can stop also, right? So that is the arrangement made with the RS, right? And then microampere to measure the current, because very small voltmeter to measure the voltage across anode and voltage of anode with respect to cathode we can have with the help of the voltmeter. So this arrangement is made, right? So one thing in the process to remember, that light energy, what is light? It is a packet of photons. We can say it is a packet of photons. So it is having photon energy. Now, each photon will liberate one electron. That is very important. So more number of photons are falling on this, more number of photoelectrons will be emitted, because 1-to-1 ratio it is, right? So more photon, if you are just projecting on the cathode, you are getting more photoelectrons which are emitted. But on the top of it, one point you always keep in your mind, that the energy of that photon should be minimum requirement. Minimum requirement is that should be as per the minimum requirement. And minimum requirement is what? This is a threshold energy, or we can say corresponding to that, it should have the threshold frequency. I mean the minimum frequency at which we can have this. If your light is less than that energy, is not going to, it is not going to liberate the electrons on the cathode, on the surface of the cathode is not going to liberate, because it requires a sufficient energy to for the electrons to come out of the surface, right? So what I discussed, I'll just note it down the points for you. The important points here are a little conceptual and subjective questions are there out of that. So I must write on the board all those things, right? So we discuss about photon, right? Where it is, this is light, right? So we can say the photons, that is the light falling on metal surface will cause the free electrons of the metal to come out. Free electrons on the metal surface to come out. Provided, what is the provided means? What is the condition? Provided the photon energy should be sufficient. The photon energy should be sufficient above the threshold value. We call this as a threshold value. If it is below that, then these photon, okay, the photons may be, number of photons may be falling on that, but this fellow is not having certain energy to liberate. It cannot liberate. What is happening there? These free electrons on the metal surface, they will absorb this energy from the photon, right? They are going to absorb the energy of these photons completely, and hence they are more energetic. So they are going to move faster in their orbit. They are going to move faster. Velocity of the speed of the electrons in the outermost cell, that is going to increase, and because of that it is likely to come out, because the centrifugal action will increase. Simple circular motion concept, right? Centrifugal action will be more than the force by the in between the nucleus, I mean the proton and that electron, right? That centrifugal action will be more, and then it is going to come out. So that is what it is happening here. Is it clear? This thing is clear to you? So for that, a minimum energy is required. That is known as a threshold value. And we know that your energy of the photon, if I take it, how much it should be. The energy of the photon, say this is your E, that must be equal to your H nu or HF, both we used to write. F for frequency, H for, this is your, do you recall? What is H here? Planck's constant, right? H is Planck's constant. In entire atomic physics, it will be used. The value is fixed. Now HF. So H value is fixed. So E will be directly proportional to F, right? It means that your E will be directly proportional to F. Means if F increases, your E will increase. So threshold value is limited to F only. The photons of higher frequency will have higher energy, so it can liberate. Now, metal to metal, a minimum, last class we were talking about the minimum energy is required to liberate the photoelectrons from the metal surface. So that minimum energy is known as the work function. In the last class we were talking about, right? So your F must be such that it at least it is up to the work function, right? That is the minimum energy required to liberate the electrons out of the surface, right? So that is known as the critical frequency, or this frequency is known as a threshold frequency. Is it clear up to that, right? So so you are saying that H being constant, E will be directly proportional to F. So from here we can say if your F is more, your energy E of the photons will be more, and vice versa, right? And vice versa. Clear up to that? So we'll go further. Now the next point we are talking about, each photon liberate one electron. One photon, one electron. That is the relation between them, right? We are having experimental setup to understand the same here. So that also we'll discuss in brief. So the point which I'll write, each photon, sorry, each photon is going to liberate one electron. Out of the metal surface. So metal surface is here out of the cathode. Cathode is a metal surface, right? Right. One photon, one electrons. Now try to understand. If the intensity of the light is more, right? Intensity of light radiation, we call this as, is more. What will happen? Intensity of the light radiation is more, means it is having more number of photons. What do you mean by intensity of light is more? Means it is having more number of photons, right? So intensity of light radiation is more. That indicates the number of photons will be more. Number of photons will be more, right? If number of photons is more, number of electrons liberated out of the cathode is more, which is known as the photoelectrons, right? So we can write number of electrons, which is known as the photoelectrons here, will be more, will be more. Now, these electrons, photoelectrons, if I am keeping a node at the positive potential with respect to the cathode, these photoelectrons is going to hit the anode. And so circuit is completed, correct? So current is set up outside through the wire. These photoelectrons, I mean the electrons are flowing, and inside this tube, from cathode to anode, we are having that photoelectrons. So circuit is completed that way, correct? And you can measure the current, we can measure the voltage, whatnot. So it means that if number of photoelectrons are more, you will find that the current is more, right? You will find that the current is more, yes or no? So we can say the current, that is sometimes we write as photocurrents also. Everything you just put the photocurrent, means inside the tube, whatever we are getting electrons flow, that will be photoelectrons. It means that photo current, now we will say photocurrent will be more. Up to that, I hope it is clear. Where we started, intensity of light radiation is more, right? The current is more. It means that out of this, all this observations, what we had here, well, I can say that straight away, if your intensity is more, photocurrent is more, right? So intensity, we'll write that if intensity is denoted by your I, right? So if I is more, right, then we'll say that current is more. Then current, photocurrent is more. Here we write IP. Got it? Because I and I we cannot write. I sensitivity, if this is more, I should just put the sign here symbolically. If this fellow is more, this fellow also will be more, and vice versa. And not only that, they are having straight linear relation. If there is no intensity of light, correct, it means no photon available. And so no photo, there's no question of photo currents. So it is a starting from origin. The line which is starting the graph, it will start from the origin only, correct? And if we try to understand on the graph, yes, you can check it on your left, the photoelectric current, right? Here it is your, we can take it, this is your IP, we can write here. And here the intensity of light, this is normally we denote by I. So the various points have been located here. If my intensity of light is increasing, obviously the number of photons are increasing. Obviously, number of photoelectrons are increasing. Obviously, the photoelectric current is increasing. So that way they are having the linear relations, correct? So, well, I can say your IP is directly proportional to I. Behind this, all all the things, whatever story we have written, behind this one point is very, very important, that the the energy of the photons must be greater than the threshold value. If it is not, doesn't matter how high you are having intensity, right? How high you are having the number of photons, but these poor fellow means they don't have the threshold value of the energy. They cannot liberate the electrons. It means the current will be zero. So all these things when I have written, IP is directly proportional to I, means photo current is directly proportional to intensity. It will be happening provided you will find that frequency is above the threshold frequency. Frequency of the photon must be greater than the threshold value, right? So provided frequency of photon, that is light radiation, out of the light radiation, must be greater than the, at least is equal to, so that it is able to liberate it, right? So must be greater than and equal to the threshold frequency. You understand the threshold frequency now, right? So corresponding to the threshold frequency, whatever energy the photon is having, that is just able to liberate the electron, and that energy which is absorbed by the electron and electron is able to come out, that energy is known as the work function. That earlier we had seen in the last class. What was that, if you recall?
The
Yeah,
maximum energy required to just liberate the phase electron out of the surface of substance.
yeah, yeah. And then what was the value, do you recall? It was your, we used to write work function as, once again we'll quickly see. Work function, you understood, it was denoted by small wo or
Yeah.
phi o, correct? So we can write now your small wo or phi o, that must be equal to how much energy? Minimum energy fo. Fo is the threshold value, where fo is the threshold frequency. Understood? Got it?
Yes.
Yeah, right? So these things up.
Done, sir.
Yes. So we got it, work function, which is your HF naught, correct? Why HF naught? Because the minimum energy required to liberate electrons is your HF naught, pertaining to the threshold frequency. That is the minimum energy, and as per the definition of work function, we can write this is nothing but HF naught. Suppose your incident radiation is having the energy, I mean the each photon is having energy greater than this HF naught, what will happen? The electrons will be emitted, that is fine. But once they come out, they will have energy left with that. Am I right? Because that W naught or phi naught, or we can say HF naught, is being used to just liberate out of the energy of the incident ray, which is where I'm telling that your F is greater than F naught. So where remaining energy will be available with the electrons, in which form? They will be in the form of kinetic energy. Am I right? They will be in the form of kinetic energy. Now these photoelectrons, once they are being liberated from the topmost surface, and not only the topmost surface, just next to it, inside also. Because if the incident radiation is having sufficient energy greater than the threshold value, is going to liberate the next layer, top layer, and the next layer also is able to liberate. Okay, those electrons will not be left out with that much of energy as the top layer is having. Correct. So once these photoelectrons have been liberated and having the kinetic energy, they are having different kinetic energy for the simple reason that they are being liberated from the one or two layers. Is not only top layer, below that also, whatever layers of the metal in which we are having the electrons, they also are being liberated. Got the case very clear? The concept very clear, right? So based on that, now we'll be discussing further. So that will keep in our mind, and then we'll be discussing further. Okay. So see this figure carefully first. What are the things here? See that carefully. We are having photoelectric current, and this side we are having anode potential, right? A was the right side. The plate is your anode potential, and left side where the photons are falling, radiation is falling, incident radiation is there. That is your cathode. Anode is normally kept positive to have a good current, right? Because these photoelectrons it is going to hit the anode, and then the circuit is completed. So right now the case is for the different intensity of the light radiation. I mean, these photons, they, if I'm considering one case one with I1, intensity I1, right? Then what kind of graph? Intensity I2, intensity I3, and so on, such that your I3 is greater than I2 is greater than I1. You see, the intensity is more, the graph is moving up. That is one observation. Why so? Because it is having more number of photons. If the intensity of light is more, incident light is more, incident radiation is more, it will have more photons. It means that it is going to liberate more photoelectrons out of the cathode surface. Am I right? And hence more photoelectric currents, photocurrents or photoelectric currents. Yes or no? So that is what it is happening here. Mind it, behind all this story, one thing you'll always remember: provided. What is that provided? Tell me. Provided. What is that provided? Do you recall? Can you help me? Provided. What should I write?
Stopping
Your
potential.
incident.
Yes.
Yeah. No. Stopping potential. Later on, we'll see. All this story we can write only if your photon incident radiation must be having sufficient energy. Right? Sufficient energy means sufficient frequency, because energy is equal to H into F. Because energy is equal to H into F. Once again, I remind you, it means that all these things should have the energy which is having the frequency greater than the threshold frequency. Correct? Then only it will happen. Otherwise, not. So for the given frequency, which is greater than the F naught. We'll have a constant frequency of the of different intensity of the light, but this frequency should be greater than F naught. So what I'm writing, I'm keeping the F constant, but this will be greater than F naught. That frequency, whatever you choose. Suppose we are having F naught as 10 to power 14 hertz. So your F should be at least greater than 10 to power 14 hertz. It may be 2 into 10 to power 14 hertz, 3 into 10 to power 14 hertz. So that way your F should be more. Any frequency, suppose I have written 5 into 10 to power 14. So it is greater than 5 times greater than F naught, right? So energy is sufficient. What it will do, it not only it will emit, it will liberate the electrons, but it will provide kinetic energy also to the liberated electrons, right? And then they start moving towards the anode. And now if I am increasing the anode voltage, what will happen? These liberated electrons will move faster, means per second more electrons will be, photoelectrons will be reaching to the anode, will be hitting the anode, so current will be more. So if I am increasing the anode potential, we'll find that current graph will also go up, right? And if it is zero, anode potential is zero, still you will find some current here, right? Still we are able to see some current is there. You can check it. If your anode potential is at O, you are able to see this cross, correct? This marker, cross marker, yes or no?
Uh, no, sir.
Yeah, no,
Oh, yeah,
yeah,
definitely. Yes, sir.
right. So if this anode potential V is zero, you will be here. Still you are having the current. See, for I1 intensity, you are here. For I2, you are here. For I3, you are here, isn't it? More the I, more the photons, and hence more the photoelectrons. And then even if your anode potential is zero, some of them are able to reach, because once they are liberated, they are having the kinetic energy, and so they will move with that kinetic energy towards the anode potential and going to hit the plate, anode plate, and so it will have certain current. Are you able to follow me? Right? So
Yes, sir.
so that's why even at zero, we are having some current. Now, one after other, I1 we had taken. For that, the graph, once I'm increasing my anode potential, the photoelectric current will also increase, right? But after some time means after a certain value of the photo and that we can say anode potential, will find that the photoelectric current is almost constant. Means beyond this point, you check it, we keep on increasing the anode potential, but photoelectrons are not photoelectrons which are released. Once all of them are able to reach the anode, then no more is left behind. All are able to reach there. So your photoelectric current will be saturating. Saturating means after that, beyond that, it will be a constant. Same photoelectrons will be just circulating in the closed path, and you will find that there is a saturation after a certain values of the anode potential, right? So beyond this point, say after this, you check it, you are finding that beyond that saturation is there, right? So same here, everywhere you'll find after this point almost is the saturation. Here you see after this point, we are having the saturation, means current will remain constant. Why so? Because all the photoelectrons which are liberated, once they are able to reach this anode potential, increase anode potential, once they are able to reach the maximum value of the current for I1, whatever current is there, right, is once they are able to reach that, beyond that, it will be remaining at the same value of the photoelectric current, right? Is it clear what I discussed,
Yes, sir.
right?
Yes, sir.
So you'll find that for this, you are getting, say, I'm writing this is your IP1, right? So for here, it is your IP2. Here I am writing the last one as IP3. So they are the photoelectric currents, IP1, IP2, and IP3. After a certain value of the anode potential, beyond that, it is not increasing. Even if you are increasing the anode potential, your photoelectric current is not increasing for the given I1, I2, and I3, right? Keeping constant V such that it is greater than threshold value. So that is there for the positive anode potential. Now, if you go to the negative anode potential, right? If you go to the negative anode potential, once I am negating, what will happen? The photoelectrons, it will be difficult for the photoelectrons to reach anode, right? It will be difficult for the photoelectrons to reach anode, right? So why it is? Because you have put the negative, so negative will start repelling them. So once they started with some kinetic energy, but other side anode you are keeping negative, so that fellow will all the time push it back, because electron itself is a negative. So it is being reduced. The velocity is being reduced, right? So once the velocity is reduced, less number of photoelectrons will reach there. As I told you, the kinetic energy of the photoelectrons which are being liberated are different, correct? So some of the photoelectrons which is being liberated out of the inner layer, they will have less kinetic energy, so they will fail to reach. Only a higher kinetic energy released from the topmost surface, they'll be able to reach, but a few of them are not able to reach if I am putting the negative potential, and hence the photoelectric current will reduce, and reduce. A point will come, that is your minus V naught here, it has been taken, your current is zero. Along the y-axis, that will is zero, correct? Current will become zero. This negative potential is known as the stopping potential, this VO negative potential, where the photoelectric current is completely stopped. Doesn't matter how much intensity you are having, it doesn't matter. Reason behind, because okay, if you are increasing the intensity, your photoelectrons have increased, but it is all depending on the kinetic energy which plays a role here. The kinetic energy of all those photoelectrons, suppose I3 is greater, okay, I3 is having more number of photons, so more number of photoelectrons which is being released, which is being liberated, that's fine, but their kinetic energy is totally governed by what was the energy of the incident ray that we have fixed, because frequency we have fixed. That frequency only requirement should be that it should be greater than the threshold value. Is it clear what I have discussed here? Yeah, is it clear to you?
Yes.
Yes or no? So I'll write all those things now, right? Once you understood, now I'll be able to write what we have discussed. So we started discussing one thing, your I1 is greater than, one thing will say that incident radiation, that is in the form of photons, mind it, is having the frequency f, having a frequency f which is greater than f naught. F naught is the threshold value, right? This is f naught is the threshold value. F naught means threshold value. Then having the frequency this much, incident radiation photon having the frequency f greater than this, R of intensities, I1, I2, and I3, such where your I3 is greater than I2 is greater than I1. Is it clear? I3 is the highest. So in I3, you will find more number of photons as compared to 2, as compared to 1. It means more number of electrons, right? So here in terms of photons, here photons in in 3 will be greater than photons in 2 is greater than the photons in 1. Yes or no? Yes, we can have this. Tell me, clear or no? If doubt, then ask me.
Got it, sir.
So if it is so, we can say the IP you understand, that is your photoelectric current we have discussed. So IP3 will be greater than your IP2 is greater than the IP3. Each photon, sorry, IP1, last one, each photon is liberating one electrons. So current will be as per the number of electrons liberated. Of course, in case of third, it will be more. So that's why we are saying your graph I3 is above I2 and the I2 is above I1, right? Clear? And then other point we'll be writing here, that is about the saturation. So you start increasing the anode potential. Anode voltage or anode potential, right? V. If that increases, what will happen? Your graph will move up. Photoelectric current IP will move up, correct? So IP will be increasing. And then we'll be writing after a certain certain an anode potential, this should be positive, right? Plus V anode potential, not a. So this is your after a certain V anode potential, you will find that your IP saturates. Saturates means it will not increase, doesn't matter how much anode potential you have, you are keep on increasing, right? So this meaning IP saturate means the photoelectric current doesn't increase, right? We'll write that photoelectric current, that is the literal meaning of current only. Here it is photoelectric current. So that will remain constant. Doesn't matter how much V, even after increasing the V, even after increasing the V. V is your anode potential, positive anode potential. So increasing the anode potential. So that's why your graph looks like this, right? Other factor, now we'll talk about retarding potential, right? Here you see in the graph, here we will have a retarding potential, right? So we'll be taking this fellow retarding potential, the negative potential. So about this we'll be writing. There is a stopping potential also, that also we'll try to understand as we have already discussed. If your retarding potential, I mean if anode potential that is negative V, right, increases. I mean, sorry, here we should write that going on the negative side. So we'll write further decreases. I mean more negative. Then what will happen? If it is so, then you will find that the photocurrents IP will reduce. IP will reduce and it becomes zero. It becomes zero at minus V naught. Potential is minus V naught, which is known as, we can write, which is known as what? Your stopping potential, correct? Which is known as stopping potential. Is it clear? So please
Yes.
note it down up to that. Yeah. So now we were talking about the V naught, minus V naught, right? V naught is the stopping potential. And at this, none of the electrons can reach. As I told you, once the electrons are liberated, these electrons, these photoelectrons, they will start moving. And since the other fellow anode is there with the positive, it was there with the positive potential, so it is being streamlined. Means all those electrons which are being exposed, sorry, which have been taken out of the surface, cathode surface, they will move towards the anode only. Now we started controlling them. I mean, we started reducing the first thing, that anode potential even below zero, means a negative side, and then gradually the photocurrents will stop, and finally will reduce, and finally it will be zero. And it will be there for all of them, I1, I2, and I3 simultaneously at minus V naught. Try to understand why it is happening. Because main idea is that the HF, the frequency of photon, I mean incident radiation, totally depends on them. Because the kinetic energy of the liberated electrons totally depend on that only. How much extra above the threshold, how much extra energy this incident radiation is there, these photons are there, and accordingly your each photon will have, minded, the each photons will have the energy. Once it is liberating the photoelectrons, that photoelectrons will have the energy which is in the form of kinetic energy, right? So it totally depends. Okay, number of photons are more in I3, but each are having the energy which is same, that is your H into F, right? So which is greater than F naught. F is greater than F naught. So these extra energy in the form of kinetic energy plays an important role for deciding the minus V naught, right? So that will be same even if more number of photons are there, even if the intensity is more, but they don't, all of them are having the same energy, and that is why all of them are liberating electrons. Now these liberated electrons, these liberated photoelectrons will have the same kinetic energy, and that is why they will be stopped by V naught. All of them will be stopped by minus V naught here, stopping potential. So that we have discussed. Now let's move ahead. Now see this figure carefully, right? Just see this figure carefully. In the two incident ray, right, 1 and 2, they are having different frequencies, F1 and F2. Minded, both F1 and F2 are greater than F naught. Because without that, we cannot have any story. We cannot write any story without that, correct? Without that, there won't be any photoelectric current. So no question of such graph. So both F1 and F2 are greater than the F naught. Now, both are having the same intensity. Both incident ray 1 and 2 will have the same intensity this time. It means they will saturate at the same point. Why? Same intensity means same number of photons in the incident radiation. Same number of photons means both of them are liberating the same number of photoelectrons. Correct? Only one of them is having higher frequency, that is your F2. So what will happen? Photoelectrons liberated number is same, but okay, in F2 we will have higher energy, right? Because F2 is greater than F1, so it will have higher energy. So more kinetic energy. That is, the higher energy means photoelectrons will have more kinetic energy. If it is more kinetic energy, we need to apply more stopping potential to stop them. because it is having more kinetic energy, is moving with the more velocity. So its stopping potential has to be greater to stop that. So this time we'll have a different stopping potential for higher frequency, means higher energy, means higher kinetic energy. So higher stopping potential will have to apply. Correct? That is what this graph says. Mind it here, your I1 is equal to I2. Remember here, in this case, F2 is greater than F2. You are able to see the cursor here, right? So F2 is greater than F2 is greater than F1, where both F2 and F1 individually, they are greater than the threshold frequency to have the photoelectric effects, right? And what is same in both the case, that is your intensity. So light I1 is equal to I2. That is what we are having here. We will have your I1 is equal to I2 in this particular graph, right? Whereas both F1 is greater than F0, F2 is also greater than F0. So saturation current, you see, we'll start from here onward. Beyond that, whatever potential, plus potential, anode potential increase, doesn't matter. Both will have the same saturation current, right? Both will have the same saturation current. At this point, it will the IP1 will be the IP2. At this point, you can see your IP1 will be equal to IP2. Yes or no? The photoelectric current, both will have the same, and that is your saturation current. Now, if I'm in decreasing my potential, anode potential, if I'm decreasing, you see that your second graph is above the first graph, correct? By virtue of F2 is higher frequency than your F2 is higher frequency than your F1, right? And hence it will have higher kinetic energy, which photoelectrons will have the higher kinetic energy. If it is having higher kinetic energy, means your current will be more, because more number of photoelectrons will be able to reach as compared to that of the first one. So higher one. Now once I'm applying the negative potential, because this fellow is having higher kinetic energy, you want to stop it. It is having higher velocity. The second one is having the photoelectrons which has come out with, they will have higher velocity. So to stop it, higher potential will be required to stop it. And that's why I'm saying VO2 is more negative than VO1, right? What is there? VO2 is more negative, more negative, more negative than the your VO1, right? VO2 is more negative than VO1. Reason you understood. So we'll just record it, what we discussed. First thing, that you're already written, I1 is I2, F1 is greater than F0, F2 is greater than F0, and your F2 is greater than F1. F2 is greater than F1, right? So we can write as your F2 is greater than F1. We'll find that your second radiation will have more photon energy, right? We can write that HF2 is greater than HF1. What do you mean by that? The second radiation photons will have greater energy than the first one. If it is so, we can say that the kinetic energy of the second one, kinetic energy of photoelectrons, rather we can say photoelectrons liberated will be more in second case, right? That we have understood. Then the first one, if it is more, means more stopping potential will be required to stop the second one. So we can say more stopping potential, that is a negative anode potential, stopping potential, which is nothing but the negative anode potential. Right? More stopping potential, that is negative anode potential for the second case, in the second case, for the second case, correct? As compared to the first one. So I'm stopping here. I hope you have understood. So a lot of small conceptual questions are there out of all these discussions. So that's why I tried to write more and more than the word written in the book. So K of the photoelectrons liberated will be more. So of course, the more stopping potential will be required. And that is what you see, VO2 is greater than VO1. I'm talking about the negative potential, right? In the figure we had seen. So this way, finally, we conclude if your F2 is greater than F1, you will get VO2 is greater than V1. Conclusion is that, right? So, well, I can conclude out of this figure, we can conclude, conclusion is that if F2 is greater than F1, right? This we are talking about the incident radiation, then we can say that your VO2 will be greater than VO1. This is the final conclusion we can say, out of which we'll have the questions. So we had seen that all these activities are possible only if your F is greater than F0, yes or no? So the last figure, you check it. If your F is frequency of radiation is greater than F0, then only you are having the stopping potential. So if you try to draw the stopping potential versus the frequency, we are going to have you check it, means after F0 only your stopping potential graph will go up. And more the frequency of the incident radiation, more the stopping potential, the just previous case we had seen, and they are having the linear relation, right? So the last one, you please note it down. This is here, your V naught stopping potential is directly proportional to the frequency of the incident ray. This is your incident ray, correct? Incident radiation. That is, I'm talking about the photon, correct? So please add on. Okay, so I'm asking one question based on the last one. Can you reply, please? Here we are having V naught. Here we are having the applied frequency, I mean the incident ray frequency of the incident ray. Now we are having two material. One material is having the graph like this, material A, right? And the other one is having your, that is, this one is giving FO1, FOA rather, right? Cutoff frequency, that is your threshold frequency, which is also known as cutoff frequency. And then we are having another one, another material B. And here the frequency FOB, right? So which material will have higher work function? Means which material will have work function means more energy is required to liberate the electrons, photoelectrons, am I right? So which material, that is your A or B, will have higher work function? Can you reply with whatever we have discussed so far? This is one of the questions that they ask. That kind of conceptual question, small conceptual questions are there. Okay, which material is having higher cutoff frequency threshold value? Which one is having? Tell me, A or B?
Sir,
Yeah.
B.
B, of course. We can see easily that my FOB is greater than FOA. Yes or no?